Okay. First of all, traditionally, I should say my deep thanks to Masashi for this kind invitation. Even virtually, it is very nice to come back to Japan. And thank you very much for this opportunity to speak here. And second, I want to say just a short excuse, because when I prepared my talk, I understood that it is absolutely impossible for 1 hour to cover all facets which I supposed to cover. So I decided to make a choice, only one, and this probably the reason was that first of all, it was one of the last, and second, we have some new results which we never say announced, and this was the reason of my choice. So my talk will be devoted to some matrix generalization of Calogero Painleve systems. And it is, of course, a very special facet of non-commutativity, not typical for what, say, Professor Retach described in his lectures, or my and Volodya Roubtsov young collaborator Irina told in her lectures. But I hope it will be also interesting and amusing. So I will speak about isomonodromy representation for matrix Painleve Calogero non-autonomous systems. First, I will remind what I'm speaking about, and then I will briefly describe Calogero Painleve correspondence in classical and quantum setting, very briefly, and then I will come to my multiparticle non-autonomous systems and their isomonodromy representation. Then the case of P2 is chosen because it is really demonstrates some phenomena of non-commutativity with respect to deformation of initial data space for Painleve systems, or in our interpretation, it is a non-commutative monodromy data space for Painleve 2. And second half of my talk will be discussed. I will discuss so-called non-autonomous analog of Rösynard's duality. Rösynard's duality, it is duality which was previously known only for the world of autonomous systems, multiparticle systems of Calogero-Moser type, and their so-called non-relativistic or Rösynard-Schneider's analogs. And because this duality demands appearance of this shift operators in Rösynard's system versus differential operators in Calogero-Moser system. We were motivated by this duality, thinking that probably the Calogero Painleve correspondence, which was very popular in the last 10-20 years, has its analog in Rösynard system as well. So it means that there is a kind of Rösynard Painleve correspondence which should be correlated with the works of Kobe school of Professor Naomi and collaborators. So my talk mainly is based on published paper with Marco Bertola from Montreal and my Angers colleague Mattia Cafassa, and on my paper with Ilya, which is submitted and almost accepted. It was accepted after revision sent it, so we are waiting final decision, and some project which is in progress right now. So I'll go to main subject. So this is a just standard reminder what I'm speaking about. List of beautiful list of Painleve 6 Painleve 5, Painleve 4, and up to Painleve 1 equations which are very well known since the 19th century, and they have a main famous property that the absence of other singularities except movable poles or movable, the only movable singularities might be poles. And this also interesting property of all these equations is that they appear in the process of so-called isomonogamy deformation. So let's consider the case, for example, Painleve 6. Painleve 6 might be represented in matrix form, like equation for holomorphic holomorphic connection, for connection in trivial holomorphic bundle, and this bundle on P1 minus 4 points, 0, 1, t, the parameter, and infinity. And residues in these points are A0, AT, A1, and residue in A infinity. Is defined by Cauchy theorem, and all matrices of residuals they supposed to be here diagonals with diagonal elements theta 0, theta t, theta 1, theta infinity, which are related to initial Painleve equation parameters alpha, beta, gamma, and delta. And this system for this Painleve case, Painleve 6 case, reduced to two Schlesinger equations, very simple system, and this system gives the Painleve condition, Painleve 6 condition for parameter lambda, which is simple poles of 1, 2 matrix entry of my connection matrix. This fact is second beautiful property, I mean this isomonogamy property, and third beautiful property of equation from this Painleve list is that all of them are Hamiltonian. And again, main income in this was done in Japanese school. Okamoto presented description of this equation in non-autonomous Hamiltonian system forms with Hamiltonians which explicitly depend on time, this complex time. In this case, this parameter t plays the role of complex time. And also all Hamiltonians, they contain the constants which relates initial for Painleve equation constants. So this representation from P1 to P6, they are due to Okamoto. And it means that your initial equation can be written as a non-autonomous Hamiltonian system in standard symplectic setting with standard symplectic form, which depends also on T. We can also admit the following very important for my talk fact, that each of Painleve equation from the list you can consider like a compatibility condition for some system of Lax type. So we have this zero curvature condition of integrability for this system with parameter z, which usually called spectral parameter. This z is a point in P1, and the integrability paradigm given by Zakharov, Shabbat, and other people demands that this is a zero curvature condition. If you find the proper matrix U and V for say, then you can reduce this condition to in each case to corresponding Painleve. So the hunting the representation of this type for each Painleve, it was well known since also Miwa, Jimbo, and other Japanese mathematicians of early 80s in 20th century. And what we want to do, we want to extend this to some other type of systems, which is also the question was raised in Japanese school, and I will mention it later. Also, it is interesting to know that there is a procedure which is called confluence. It is just geometrically, you can imagine it like a colliding of singular points. And this confluence permit to write degeneration one Painleve equation to another Painleve equation. For example, P6 to P5, and P5 in two different ways may be considered like a degeneration procedure with Painleve 3 and with Painleve 4. Here is a diagram which is also belong to beautiful observation Japanese mathematician Sakai, who wrote this diagram and explained it in terms of affine Dynkin systems. So you have assigned to each vertex of this diagram, you can assign some affine Dynkin diagram of type D or of type E of type F. So this is a three Painleve three equations. In fact, it is just three different possibility to represent Painleve 3 in this isomonodromy, in this zero curvature system compatibility. And each possibility corresponds, due to Sakai, to Dynkin diagram D6, D7, and D8. And other degeneration also you can follow by this Sakai diagram. And this diagram, it is geometrically very transparently can be described in the following. This idea came to our head with my colleagues Marta Mazzoka and Leonid Chekhov. So we just interpreted this diagram like a diagram of corresponding monodromy surfaces, monodromy data surfaces for our Painleve systems. For example, it is known that monodromy data surface for Painleve 6, it is just sphere with four smooth borders around four punctures. So you take 4 points on sphere and you take border of each puncture. And these borders are smooth circles. But now let's suppose that this sphere, it has some material which is can be deformed. Like, for example, I'm sorry for this maybe not very nice explanation, but you have chewing gum, and you can imagine that this chewing gum you can deform in all directions almost to infinity. So if you start to put one border to another border, and then how to do it? You just take this surface material which is between two borders and start to go to infinity. All this description can be done explicitly in terms of hyperbolic geometry. I will not go into details, but after this procedure, at some point your chewing gum surface just has a break, and you have two such what we call cusps. And then instead of two smooth border, you have one border with two singular directions. So this surface deformed in the surface with non-smooth border. And this phenomena, in fact, in the language of equation, corresponds to multiple poles, because when you have this collision, when you have this confluence procedure, you have instead of poles order 1, poles order 2 here, and to this pole there are no good monodromy data. Instead of this appeared so-called Stokes data, so this is a geometric interpretation of Stokes phenomena. And then you can do the same procedure. For example, you can make again two borders collide, and you have Painleve 3d6 with two borders and two infinite directions. So you have all this description may be done also analytically and algebraically. Algebraically, it means that you can write the surface like a cubic equation, and all this deformed, or if you want, confluent monodromy surface, they are also some cubic surfaces. It can be described very nicely and very long. I have no time to describe it in more details, but I want to say that there are two different operations, just to draw your attention that there are red and green arrows, and these arrows they respond to different operation. A red operation, this operation I described, it is just a collision of two borders. And green operation, it is collision of two singular directions. And you can collide each two singular direction to one. You can't eliminate one. So you can't make your border smooth after this non-smooth collision. But you can reduce number of these cusps. And the difference between even and odd number of these cusps, it's a difference, if you want, between regular and irregular singularities. So it is just poles. Then you have this Stokes phenomena, and in each Stokes sector, your solution will have a different type of behavior. Ramified singularity and non-ramified. So bad case when you have only one such direction. This bad case means that your singularity is ramified. It means that this corresponding for those who are in the business, it corresponds to a fractional cuts index, and even has a integer, even number of these cusps has this. I spoke about it because one of results of our theorems with Mattia and Marco, some non-commutative analogs of these surfaces, which unfortunately we made very explicitly only for Painleve 2 case. Painleve 2 also have two different Lux representation, so-called Jim-Bamiva representation and Flash-Newell representation. So we more on this deformation of cubic for Flash-Newell. It is slightly less difficult than very beautiful description of isomonodromy surface of Jim-Bamiva type. Okay, now I go to the main subject of the first part of my talk, namely, what is the Calogero-Painleve correspondence? It was well known, so it was well known even to Painleve that Painleve 6 can be written in very nice special elliptic form. Namely, if we have an elliptic curve in this Legendrian form with parameter t, and we can associate with this curve the Weierstrass p function with double pole in 0. So we can define the for modular parameter tau, which is tau. It is just you have your curve. It's a quotient of complex plane over lattice with some generators 1 and tau. So you have this summation over points of this lattice, and then you can define 3 values of p function in the point omega 1, omega 2, omega 3, where omega 1 it's 1 over half, omega 3 it's tau over half, and omega 2 it's minus arithmetic average arithmetic value, mean arithmetic value 1 and tau is minus. Then it was even known to Fuchs, Father, and Painleve, and to Lamé, French mathematicians, and then rediscovered, not rediscovered, but with beautiful hint of Yuri Manin, that this coordinate q, which can be defined explicitly from this data, E1, E2, and with q dot defining like a derivative over the modular parameter tau, then the Painleve equation can be written also in Hamiltonian form, with Hamiltonian, which is completely described by this combination of values of p function in this data omega 1, omega 2, omega 3. And this Hamiltonian has a natural form. Natural, it means the dynamical part is quadratic, and interaction part, depending on tau, like on parameter of non-autonomousy. So it's Hamiltonian explicitly depend on tau. And it is so-called Lamé form, because I think that Lamé was the first who discovered the equation which correspond to this Hamiltonian. And constants in the interaction part, it is just alpha, beta, gamma of and delta of initial Painleve 6, which are related to this constant by this formula. I want to say that immediately Manin had the idea that probably it is possible to find for any Painleve equation the form of such type. Q double dot equal to minus V Q T. So where this potential function explicitly depend on T. So to find representation of each Painleve in Hamiltonian form with Hamiltonian HPQT, which has natural form P square plus V Q T. So it was a question. And then this was done because almost immediately after maybe a couple of years, it was in 2000 or at the end of 90s, my colleagues, former colleagues, because neither me nor them, they are not in this institute, but at that time it was a very famous Moscow Institute, Institute for Theoretical and Experimental Physics, Andrei Levin and Mikhail Olshanetsky, they observed the following thing. They consider Manin Hamiltonian for Painleve 6, and this Manin Hamiltonian they interpreted like a rank 1 case of many particle system, which was introduced by another Russian theoretical physicist, Inozemtsev, with this dynamic quadratic part, p square over 2, and the interaction part is a combination of different values of p function. But Inozemtsev considered this like just a generalization of elliptic Calogero-Moser system, and he didn't consider this system like non-autonomous. He ignored the parameter tau like a time. And Levin and Olshanetsky said, okay, if we take Manin Hamiltonian and we'll consider this Inozemtsev and take the autonomization of Inozemtsev for the case of rank 1, when we have only one Q, then we obtain explicitly Inozemtsev autonomous system. If we autonomize Manin or deautonomize Inozemtsev, we obtain Manin Lamé Painleve 6 Hamiltonian. And it was a starting point to study Painleve equations in so-called Calogero-Painleve correspondence form. The next representation of what I showed you here was done by Zabrodin and Zotov. Zotov was at that time a PhD student of Olshanetsky, but Anton Zabrodin is very famous physicist and mathematician. They proposed such form for all other Painleve in classical and in quantum setting. Kanehisa Takasaki revised this Painleve Calogero correspondence almost immediately after observation of Levin. Namely, he wrote this Hamiltonian for many particle systems with some potentials, which in one hand side can be considered like Calogero-Moser type potential, and in other hand side, they depended on time explicitly. And then he proved that there is a canonical transformation of such non-autonomous Hamiltonian to the list of Okamoto Hamiltonian, which were known before. So he established a bridge between Calogero-Moser system and Hamiltonian of Calogero-Moser and Okamoto Hamiltonian in this non-autonomous case. So it was a very important observation because even independently to the theory of Painleve, such model of non-autonomous Hamiltonian Painleve Calogero type system in the case of Painleve 6 in 2005 was considered in the paper of Ettinghoff, Gan, and Oblomkov in the connection with so-called generalized double affine algebras in higher rank. This is not occasional observation, because in his thesis, Oblomkov proved that quantization of monodromy data for Painleve, it means quantization of function on the cubic, which I showed you, this cubic with four smooth borders. So this is the surface, smooth surface with P1 minus 4 points. Then you consider algebra on this function algebra on this cubic, and this cubic has the form x, y, z plus x squared plus y squared plus z squared plus omega 1 x plus omega 2 y plus omega 3 z plus omega 4. This affine cubic. This equation was known to Klein and Fricke in 19th century, and in Painleve setting it was appeared in the paper of Jimbo in 1980. So how to quantize this algebra function? This surface admit some Poisson structure. It means that you can write Poisson bracket starting from this cubic, considering like a Casimir. For example, if you take a bracket between x and y, it means that you should take partial derivative of this polynomial over z, and then by cycle you obtain all algebra, Poisson algebra on structure on the functions on this surface. And then Oblomkov proved that when you quantize it, you obtain non-commutative algebra, and this non-commutative algebra is explicitly double affine Heike algebra in sense of Cherednik. So such representation was very important ingredient of the theory of non-commutative Delpezze surfaces in the theory of Ettinghoff and Ginzburg. And then we extended with Chekhov and Marta in our paper 2020 in advances. What was Kanehisa Takasaki input? He wrote explicitly higher rank Hamiltonians, so not only for rank 1, and this was generalization of Inozemtsov autonomous Hamiltonian, in the case Painleve CX, and then all other Hamiltonians for Painleve Calogera. You see that these Hamiltonians can be conditionally represented. I put it in different colors. So they are red. This is a simple part. This simple part corresponds to Calogera-Moser analog, which people call usually rational Calogera-Moser systems. This blue color, it's Painleve 3 and Painleve 5 Hamiltonians. They correspond to Calogera trigonometric, or in this case, it is just hyperbolic, but it depends on the choice of group. And then, I mean, many particle symmetry group. And then this orange, it's in some sense master Hamiltonian, and this master Hamiltonian is elliptic. So you have elliptic Calogera-Moser system, or more precisely in this format, generalized Calogera-Moser. If you fix tau, it's Inozemtsov. And then hyperbolic in the case of H5, H3, and rational H4, H2, H1. We, in our paper, we give the answer to the question which Takasaki asked. Can we, for this multi-particle non-autonomous Hamiltonians, find Lax representation, matrix representation for zero curvature condition for the equation associated with this Hamiltonian? This question was open 18 years, and in 2018 we published a paper where we give the answer, and we related this. This question to the question of so-called non-commutative matrix Painleve Hamiltonians, which appeared a couple of years before in the paper of Kawakami. So what we propose? We propose isomonodromy description, which gives answer to the question of Kanihisite Kasaki. And then we consider what output of this we can gain. Well, quantization, it means deformation of the initial classical monodromy data space, which I briefly discussed. And then we also used this to define Rosinar's type duality. The main observation was very, very simple, in fact. Observation was that if we take classical Hamiltonian reduction of Kazhdan, Kostan, Sternberg, which they applied in the autonomous case to Kalogero-Moser system, to this Kalogero-Painleve, it works perfectly in matrix setting. So it's, if you want, it's matrix analog of Kazhdan, Kostan, Sternberg reduction. I choose to show you just the simplest example of P1 because formulas, other formulas are very, very tedious, and here they are not simple as well, but anyway. So we have this, its answer for the case of Painleve 1. We have this matrix. This matrix, Lax matrix, it's a block matrix. Each entry of this 2 times 2 matrix, it's n times n matrix, when n is a number of particles, so p, q, and when I don't write, for example, z square and t o, o, I suppose that they multiply by identity matrix n times n. And then this zero curvature condition, integrability, can be reduced. This system can be reduced in coordinates q and p to matrix system of Hamiltonian type, which depends explicitly on T. Geometrically, what does it mean? Geometrically, it means that we can try to play with these equations, with these 2 equations, in the game which people play in the case of usual Kalogero rational system. So they have a phase space of free system without any constraints. And this phase space is T star to Lie algebra GLN. This phase space is a symplectic with canonical matrix 2 form, which given by dq wedge dp, and then to give usual form, you should take a trace of this matrix. And the corresponding Hamiltonian, it's Hamiltonian which depends on T explicitly. So this Lax equation admits this form with this Hamiltonian with respect to this symplectic structure. And it is not difficult to verify that the PQ commutator plays the role of so-called angular momentum, and it doesn't depend explicitly on time, so it's a conservation law. Then the philosophy of Hamiltonian reduction, which goes back, as I told you, to Kazhdan, Kostan, Sternberg, gives you the following reduced phase space. This reduced phase space, it's a level when commutator, which is, I remind you, doesn't depend on T now, has a special matrix form, rank, so-called rank 1 matrix, with a constant G4. It's just remind you that this G4 came from initial numbers of innocence of parameters. Anyway, it is just an interaction constant, like in Kalogero case. And then it is not difficult to check, like in the case of usual reduction, that when we take Q diagonal, then there exists this gauging matrix G, which diagonalizes it. And applying this matrix to P, we obtain the equation for commutator of this X and Y, gauged matrices X and Y on this form. And as a corollary, we can compute form of this gauge, new form of this gauge matrix Y for P. And as I told you, Q is diagonal. So you have the standard coordinates, like in the case of rational calogera, or we have symplectic coordinates on the orbit of this. We can interpret geometrically this commutator with the help of this commutator, the moment map in dual vector space to our algebra G star L. So now we have a reduction, and this moment map gives you coordinates on the symplectic coadjoint orbit, which correspond to diagonal matrix with diagonal entries -1, -1, -1, and -1. So this choose of trace equal to 0, but that's why we take this special, it's a PGL case. So this reduction can be applied to our problem for Lax pair choice. Of course, now in our case, gauge transformation should be non-autonomous. So we have this version of gauge matrix G fed and eigenfunctions solutions of this system. They are under this non-autonomous matrix action. So we can apply this this gauging to our form which we have, matrix form. We obtain new after gauging using this lemma for X and Y matrix elements. And we solve this problem and obtain the answer for non-autonomous system. And then you can write the equation after gauging in this form. And this exactly equation which you obtain if you write this in the form of Hamiltonian system for Q and P with Takasaki Hamiltonian. Or, in other hand, if we take our non-commutative Hamiltonian, we can write it in this Takasaki form, applied our, and this is very well corresponds, and just a small canonical transformation transforms this equation in Hamiltonian form with this Takasaki Hamiltonian. So it works like this. And instead of write all of this, I just refer our paper with Marco and Mattia. You can find such representation for all other Painleve. But I just want to show how it collides with the results of Kawakami. If you consider now any Fuchsian systems, a system with simple poles and residues AI, not with 4 points like in the case of Painleve 6, but for n point, and we impose the same condition on the residues, that each residue matrix is just a diagonal matrix, but maybe with some multiplicities, and with this Cauchy residue condition, then to each point, each pole, including infinity, we have residues, and we have this set of multiplicities. And this set is called spectral type. The number of accessory parameters gives you the dimension for phase space of this system. And this is given by the famous Katz formula, this very famous Katz formula, which, for example, works for our case for Painleve 6, just to illustrate it, as follows. We have 4 points. We have simple poles, so we have multiplicity of each eigenvalues 1, 1, 1, 1, 1, 1, 1, 1. And then the spectral type of Painleve 6 we can compute by this Katz formula as the follows. We have n here equal 4, because we have 4 points. K here we have 2, rank 2, 2 times 2. So we have 2 times 4. This is the case. And then we have minus number of, for each point you have a sum of squares for multiplicities. For each point you have 1 square plus 1 square, 2. 1 square plus 1 square, 2. So here you have 4 times 2, 8. And then you have 2 minus 8, 6. And here you have 2. Here you have 8. And then 8 minus 6, you have 2. That means that you have a surface for Painleve 6 with 4 points. Then the first example of higher rank in the case of rank 4 was proposed by Ashima, and Ashima considered the Fuchsian systems with 4-dimensional phase space. So he had so-called Garnier systems, and one of them, it is just usual Garnier with simple eigenvalues multiplicity 1, and then also some examples of system with eigenvalues multiplicity 2, eigenvalues multiplicity 3, and then this was the case which correspond to 4-dimensional analog of Painleve 6. Kawakami generalized this Ashima example for n equal to 4. He generalized it for any n, and he gave a matrix version of Painleve 6 and corresponded conference procedure. It looks like this. So now we can consider Kawakami case. Instead of case n equal to 2, we have block matrix. You see, block matrix. These residues in each point 0, t, and 1. They have a block matrix with entries n times n. Theta's, they are only times en, and of course it is diagonal matrix in this low right corner, and corresponding infinity residue matrix also diagonal with this set of data. And then Kawakami consider the following theorem. Let's compute PQ commutator in terms of our diagonal data. And then this system admit isomonodromic deformation of system with Hamiltonian, which is analog of H6 Hamiltonian. Namely, you take non-commutative H6 Hamiltonian. You see now Q and P are matrices, so it's n times n matrices. And this is a data from initial Painleve 6 Hamiltonian. So Kawakami system is isomonodromy deformation for this Hamiltonian. And we proved that all Kawakami matrix non-commutative Hamiltonian, they are correspond with respect to description of our reduction with PQ constant to the Hamiltonian Takasaki in the isomonodromy representation. That was the main output of our paper. So we have a Calogero Painleve system from one hand side with a Komodo Hamiltonian of Takasaki. Then we go to isomonodromy representation, we obtain non-commutative Kawakami Hamiltonian for corresponding non-commutative Painleve system. Okay, now what's the output of this? Let's consider the deformation of monodromy data. So we have this representation for Painleve 2, this matrix representation for Painleve 2. And I want now to establish small link to what Retach and Irina told you before. So if we introduce the vector time, namely consider diagonal matrix with diagonals T1, Tn, and generalize d over dt like derivation over a vector dt, like a sum of derivations to each component, then we can write the Painleve 2 equation in non-commutative form with anti-commutator instead of second term. So this was our initial proposition with Retach, but we considered it like just a toy model. We just considered it like a toy model because we were very much inspired by link with Hankel determinants and Toda non-abelian Toda system. But 6 months or maybe even less after our preprint appeared, I received a letter from Mattia Cafassa, and he told that with Bertola, they found explicitly our non-commutative Painleve 2 equation, which was the result of their approach to Riemann-Hilbert description, Riemann-Hilbert description of some problem related to its Karepin-Slavnov computation of correlation functions with the help of Fredholm determinants. So now I want to formulate the theorem of solution of this matrix Painleve 2 system using our observation with Mark and Mattia. So now we are in the situation with Stokes phenomena. So we have Stokes sectors and Stokes matrices. They give these 3 operators, which in each sectors written in block form as well. And relation between Stokes operators, they gives you non-commutative version of isomonodromy surfaces. So this, in fact, one surface and commutation relations between non-commutative Stokes where parameter Q, it is also a matrix, exponent E P times commutator PQ in our Lux representation. Then I want to make a confession that in our paper, these relations are written with a small mistake. And this small mistake, a couple years after discovered Irina made all computations more carefully, and she discovered that we made a very stupid error in commutation of metrics. It is not ideologically nothing changed, but it significantly simplified our formulas. Here I give you only one non-commutative equation. And in our paper, there are two non-commutative equations plus non-commutative commutation relations, which slightly more than this. But now everything is very well compatible with classical case. Now, if you take the classical Flaschke-Newell Lux pair for Painleve 2, then the monodromy data can be written in the form of this cubic. And you see, this is just usual commutative variables. This is a constant, which is relates to one parameter of Painleve. And in the limit, you obtain from our, you can obtain this classical cubic variable. What is interesting that in our erroneous formulas, in the limit, they also give this, but with changing of cosine by sine. Now, it is also very nice because if we take special degeneration of our commutation relations to commutative Stokes matrix data, then we have this nice commutative surface. And Bertola and Cafassa, they also indicate how this trace of Q square related to their determinant of Fredholm in the computations of correlation functions in its Slavnov-Karepin model through the matrix Airy operator. This is a formula from their paper of 2011. And then you can use it to compute very nice asymptotics in terms of Airy function, which correspond to this degeneration of solutions of Painleve 2 classical usual scalar solution to Airy scalar on matrix level also gives you degeneration of these solutions, matrix solutions of Painleve 2 to matrix Airy. This was a nice paper of Mattia and Marco. And our deformed cubic, as I told you now, is very, very simply written due to Irina correction. And commutation relations gives you the relations which we obtained with Marta in 2012, and we call this Terwillinger-Ito relations for representations, equitable representations of quantum group UQSL2. Okay, what the output of this? You can ask. The output was formulated by Alexander Itz when I gave these results in Montreal in 2019. It said, oh, but it is beautiful because now integrability in sense of zero curvature, Lux integrability, and then representation solutions through Riemann-Hilbert data, like it was in Cafassa Bertola case. It is very important because it gives you possibility to give some asymptotic behavior of so-called Tracy-Widom distributions for beta ensemble beyond the classical values of beta 1, 2, 4. And immediately after our paper, they with Prokhorov started this asymptotic analysis, and using our formulas and this Kalodger-Painleve system, they computed Tracy-Widom distribution function for beta equal to 6. So I'm very glad to help with this. How much time I have? Almost I have no time. Yes.
Yeah, but it's flexible, so please continue.
Well, I'll try to be very, very short. So what I mean under duality and what we did with Ilya and what Ilya beautifully computed himself. First of all, what I mean under this duality. We discovered that in paper of Rosinars, there is some kind of action angle correspondence or action angle duality for many particle systems of Calogero-Moser and the Rosinars-Schneider's type. So two integrable many particle systems, we say that they are dual each other if it was a proposition of Rosinars, the action coordinates of action variables of one integrable system. So we have action angle representation for each integrable system, and then we can have exchange between actions and position coordinates for first and second system, and vice versa. And it means that you have that the phase space symplectomorphic or anti-symplectomorphic up to sign. The first example of such duality was, of course, very, very simple self-duality in the case of rational Calogero system. This self-duality means that when you write this constant Kazhdan-Sternberg reduction, you can diagonalize Q and compute P after gauging. And you can also diagonalize P and then compute Q. And then you will find that the Hamiltonian are the same with the change in P and Q. And symplectic form just change the sign. And it was observed by many people, for example, in the beautiful paper of Ero, McKin, and Moser, when they studied behavior of rational poles of solutions of KdV hierarchy, and then they discovered that between these poles which are governed by Calogero-Moser, there is some kind of self-duality. Then Rosinars extended it to all other many particle systems with including relativistic version of Calogero. So this was a situation in the mid-90s. In mid-90s, we with Gorsky, Nikita, Nekrasov, and Fogg started to link this duality with the topological field theory, with some kind of n equal to 2 supersymmetric field theory. And on the level of integrable sector, we always have Calogero-Moser Rosinars systems. So we wrote big paper in 2000. And then in this paper was observed that if we take rational coordinates, trigonometric coordinates, elliptic coordinates in row, and rational moment, trigonometric moment, and elliptic moment in columns, then between rational Calogero system, there is a kind of self-duality. But if you take trigonometric Calogero system, then the exchange P and Q in the momentum equation gives you a new system, and this system is no more differential if you go to dynamical part. Instead of P, you should put shift operator. And this operator gives you rational Rosinars Hamiltonian. If you go to trigonometric Rosinars, then it is again self-dual. So change, it is not simply to show, but it is possible. And then the question was very tempting question, what is the dual to elliptic Calogero? So there is some kind of dual elliptic Calogero. And what we will have for elliptic Rosinars and dual. Now the answer to these questions more or less understand it, but the question about dual system is still as far as I know, open. There are many new results about this system in classical and quantum case, but explicitly you can do it only for a small number of particles, but in general, the results only conjectural. So this is what we have in the level of usual classical system. So this example, what I just mentioned very quickly, this Calogero, rational Calogero, you see dynamical part, interaction with rational, because it's rational function and positions in square of positions. This is my momentum equation. And then self-duality of rational Calogero means that after diagonalization of Q, you obtain the Calogero system. If you diagonalize P, you obtain again Calogero, but P and Q will change places, and the corresponding symplectic form change sign. So this is what you see, DQP. This is new system, which is diagonal in P and Q computed by similar formula. So this is what we had. Now, what's interesting question, what's happened if we go to this matrix Hamiltonian, and can we find this duality in the case of non-autonomous system? With Ilya, we we computed dual Hamiltonian for H1, you see, and it has this Hamiltonian in P square and Q cube, and TQ1 depends on T, and the interaction part is this, it includes both P and Q. So it's a kind of new Hamiltonian non-autonomous system, unknown before. And if we take Painleve 4, then we have even more interesting new dual system. This dual system, which we discovered, it is no more pairwise interacted like it was in Calogero, Schneider, Ruisenar's case. It is 4-point interacted. You see, this term includes 4-point interacted system in dual coordinates. This is also unknown new Hamiltonian system. So this 4-particle interaction. If we take Calogero Painleve 4, then we have what we have. We have self-dual. So it is interesting that for Painleve 4 dual system, it admits self-duality like in the usual case. This is the dual H4 Hamiltonian, and this after change of variables, canonical change of variables, we obtained the initial Hamiltonian which we had. This was what we had with Ilya in our paper, and then in duality we have the same Hamiltonian when P and Q change the place. But what we observed, it was new phenomenon. If the conference map for matrix Painleve 4 gives you matrix Painleve 2 like it was in usual Painleve case, then when we go to dual system, then dual Painleve 4 can't be confluently degenerate to dual Painleve 2. Moreover, dual Painleve 2 looks much more complicated than dual Painleve 4. So we have some real obstruction. We computed this real obstruction with Ilya. And then it is new phenomena which should be studied. What's happened under with a conference in matrix case with the duality. And then Ilya computed what people expected, like Painleve-Ruisenar's correspondence. We had before Painleve Calogero, now we have also possibility to change rational. You see, all these systems, why I spoke about 1, 2, and 4, because they correspond to rational models. What's happened if the model is not rational, but trigonometric or elliptic? It looks very, very amusing. So first of all, we should change the phase space. Instead of T star of GLN, we should take the Zariski open part of this, where determinant, say, Q, matrix Q, and different from 0, and then change of coordinates. And this change of coordinates change the form from T star of algebra to T star of group. It was expected even in our paper in classical case with Gorsky, Nekrasov, and Fogg. And this form has this exact type, and the corresponding Liouville form is a group type. And then when you compute the coordinates in no more canonical, but they are log canonical. So they are dp wedge dq over q. So it's log symplectic coordinates. And the reduction for Painleve 3d8, the case which Ilya computed up to the answer, this gives you standard Painleve matrix, Painleve with matrix omega, which we described in our paper with Bertola and Kafasa. And then after changing of variables and going to the level of momentum of this half group momentum, Ilya compute new P tilde and Q tilde, which further I will again define just P and Q. So after this reduction, this Hamiltonian comes like this. This, with respect to log symplectic form in these new coordinates, this Hamiltonian can be written also in the form with trigonometric Calogero Painleve with new time t. And if you make change of t with this strange transformation with square root of t, then your form becomes extended non-autonomous form, but the Hamiltonian with this square root of t change its form and gives you this additional term which we had known before, this g plus g minus 1. And immediately here I recognize, I said, oh, this we know with Gorsky, Fogg, and Nekrasov, it should be Roy-Senars. And if you write it in new coordinates g tilde by this transformation, so you transform Hamiltonian of d8 in the Hamiltonian with p square and g of Roy-Senars type. So this one can say that this is a rational Calogero Roy-Senars Hamiltonian. So we have from Painleve D4, we have rational Roy-Senars system. And also, it is very interesting that if you take D7, then D7 also admits the same, but Ilya didn't finish yet computations because we started to do something else, and these computations we postponed. We computed how from this hyperbolic Painleve 3d7 in new coordinates, now diagonalizing p, we can obtain new Calogero Roy-Senars Hamiltonian, which make certain that this correspondence can be extended to Roy-Senars systems of also of not rational, maybe trigonometric type. What's happened with elliptic? It's absolutely unclear now because we don't know how to handle Roy-Synapse elliptic case in our setting. It's a more complicated reduction. So thank you very much, and I'm sorry for 15 minutes of delay.
No. Okay, thank you very much for very interesting talk.